So the next thing we're going to talk about is how do you figure out the G value, the G force as they call it. The acceleration due to gravity. Where did that 9.80 come from? In fact, I've been seeing a lot recently that it's now become 9.81 meters per second squared, whatever. Maybe the mass has changed, maybe the radius has changed. Radius of the Earth may be shrinking a little bit, so that would tick it up just a little hair. Very possible. Regardless, here we have an idea based upon Newton's law of universal gravitation. So there's going to be a lot of math in this. One of the things that you are going to be asked to do later on, not necessarily in this class, but in the future, if you're involved in a physics-related major or activity or engineering, you're going to have to do a lot of derivations, equations, manipulations. So this is going to be a good exercise in that. First of all, F equals Gm1 m2 over d squared. This is Newton's law of universal gravitation. We also know that F can be found when taking ma. Okay, that's the second law of Newton's laws of motion. Second law of Newton's motion. Whatever. Newton's second law of motion. You know, one of them things. Alright, so I'm going to set these equal to each other. So ma equals m, sorry, got the G m1 m2 over d squared. Now, what I'm going to do at this point, and I'm going to start taking the scenario that little g is talking about. It's like force of gravity of me, a person, getting sucked to the center of the Earth. Okay? So that's where this is going to come in. So I'm going to, and since the relationship is between me or you or whoever and the center of the Earth here, M1 is going to be this M right here. M2 is going to become E, Earth. And D squared will become the radius of the Earth squared. We're going to use the equatorial radius. There's two radii mentioned in the book. We're going to use the equatorial. Okay? Now when that happens, M1 cancels out. What leaves is A equals G M sub E over R squared. Radius of the Earth squared. So it's not ambiguous. Since we're dealing with gravitational attraction, then this becomes G. Same thing, acceleration, only this is due to gravity. Alright, so if we go to the book and we find the various values, where do you know G? 6.67 times 10 to the negative 11 meters per kilogram squared. The mass of the Earth here is 6.0 times 10 to the 24th kilograms. And the radius of the Earth is like around 6.4 times 10 to the 6th meters. And this is going to be squared. Like I said, this is 6.67 times 10 to the 11th Newton meters squared per kilogram squared. Plug all that nonsense into your calculator, and sure enough, you'll get somewhere in the neighborhood, I think, 9.8 meters per second squared. Now, in actuality, I think this is 6.38. I think they rounded off, and that caused it to be slightly off. I think it had 979, and I think you get 980. It's 6.28. It's a slightly smaller denominator. All right. So regardless, there's the proof that of how we got our G. Okay? Now let's suppose, and this is the first example, let's suppose I want to find the G of Jupiter. G sub J. And so, I'm going to have to use that formula. G, and it's a constant, so it's going to stay the same no matter where. Universal law, blah, blah, blah. The mass of Jupiter over the radius of Jupiter squared. So, 6.67 times 10 to the Negative 11, I'm looking at the wrong number. Newton meters squared per kilogram squared. Meters squared per kilogram squared. Times. And then the mass of Jupiter, I looked it up, is 1.9 times 10 to the 27th kilograms over, and the radius of Jupiter is 71,500 kilometers, which is 7.15 times 10 to the 7th meters. And that's going to be squared. Get that square, punch that all into your calculator, and you get a value of 24.8 meters per second squared. 2.5 times the gravitational attraction of Earth. So, if someone from Jupiter, if there was a person from Jupiter came over to Earth, that person would probably leap over tall buildings in a single bound. You know the story. All right. So,